Amazon's global data centers used 2.5 billion gallons of water in 2025. The company confirmed this for the first time in June 2026. Google consumed around 8.1 billion gallons in 2024, with about 95% used at data centers. That's an 8% increase from 2023, and Google's consumption had already nearly doubled over the 3 years before that. Training one of today's largest artificial intelligence systems required approximately 700,000 liters of water for on-site cooling alone. When the water used to generate the necessary electricity is included, the total rises to around 5.4 million liters for a single training cycle. The next generation of systems operated on an entirely different scale. One major data center cluster in Iowa consumed 11.5 million gallons of water in July 2022 and 13.4 million gallons in August during large-scale model development. Every time you interact with an AI assistant, resources are being used behind the scenes. Roughly every 20 to 50 prompts can consume about 500 milliliters of water, the equivalent of a single bottle. With more than 1 billion messages processed daily across popular AI services, that adds up to an estimated 148 million liters of water every day. That's enough to fill around 59 Olympic-sized swimming pools every single day. Some estimates suggest that one widely used multimodal AI system evaporates enough fresh water each year to satisfy the annual drinking needs of 1.2 million people. By 2027, global artificial intelligence operations could consume between 4.2 and 6.6 billion cubic meters of water annually. For perspective, that's roughly 4 to 6 times the total water consumption of Denmark in an entire year. Data centers use water in 2 ways. The first is direct, evaporative cooling systems, where water absorbs heat from servers and then evaporates into the air. It's cheap and effective, but that water is gone. It doesn't go back into the water table. The second is indirect. The power plants generating the electricity that runs the data centers also use water for cooling. This gets ignored in most discussions because it's off-site, but it's part of the real footprint. The idea has been floating around tech circles for years. Antarctica is cold, genuinely, permanently, brutally cold. If data centers consume huge amounts of water to keep servers from overheating, why not move them somewhere nature already provides the cooling for free? No giant evaporative systems, no strain on local water supplies, just endless cold air doing the work. At first glance, it sounds like an elegant solution, but once you move beyond the surface, the picture changes quickly. The biggest obstacle appears before a single server even arrives. Antarctica isn't simply empty land waiting for development. It's governed by an international agreement signed in 1959 and supported by dozens of nations. The continent is reserved for peace and scientific research, not commercial industry. Turning part of it into a hub for private AI infrastructure would collide with decades of international cooperation and environmental protection. Even if that barrier disappeared overnight, the cold itself isn't the effortless advantage people imagine. Electronics love stable conditions, not extremes. Temperatures that plunge far below freezing introduce new engineering headaches: condensation when equipment warms, ice formation inside systems, and constant thermal expansion and contraction as machines cycle between operating temperatures and the surrounding environment. Instead of fighting heat, engineers would spend enormous resources fighting cold. Distance creates another challenge that no amount of technology can fully erase. Antarctica sits thousands of kilometers away from the world's largest population centers. Data may travel near the speed of light, but those extra milliseconds matter. Modern AI tools, cloud services, gaming platforms, and financial systems all depend on rapid responses. Add enough geographic separation, and the user experience begins to suffer in ways that people notice immediately. Then there's the question that every data center eventually faces. Where does the power come from? Cooling is only one piece of the puzzle. Massive computing facilities consume staggering amounts of electricity around the clock. Antarctica has no interconnected power grid waiting to support industrial-scale operations. Every possible solution comes with serious limitations. Shipping fuel continuously across some of the harshest seas on Earth would be expensive and environmentally damaging. Large-scale renewable projects face extreme seasonal conditions, while other energy options run into legal and political barriers. The infrastructure required would rival the complexity of the data center itself, and even after solving all of that, the practical reality of maintenance remains. Modern server farms survive because replacement parts, skilled technicians, and supply chains are always close by. In Antarctica, none of those advantages exist. There are no major industrial ports, no local workforce, and no nearby warehouses filled with spare hardware. Something as ordinary as replacing failed equipment could become a logistical operation involving ships, aircraft, weather windows, and weeks of delay. So the real path forward probably isn't about moving AI systems to the most remote continent on Earth. The more realistic solutions are already emerging. Cooling technologies that recycle water instead of consuming it, facilities built in regions with abundant renewable energy, smarter software that uses computing resources more efficiently, and designs that reduce environmental impact from the start. Whether engineering innovation can keep pace with the explosive demand for artificial intelligence, that's the question that will shape the next decade. That's it for today. If this kind of breakdown is useful, subscribe and hit the notification bell. See you in the next one.